Hello.
Hello, everybody.
Hello.
Hello. We are 13 already, yeah?
Maddie is here. Hi.
Hello.
There's Maddie. Have you met Maddie before, guys?
Oh.
There's Maddie. Hello.
I remember we were together with Ralph and with Janos in Coventry University in London. Also funny name.
Oh, that is a long time ago. That was a
Yes,
long time ago.
it was some conference, and
Yes, yes.
you were giving talk about how, in fact, how disease spreads, about disease spreading.
That I don't remember. I remember that some years ago there was a conference in Coventry. What I talked about that.
Yeah, but it was Coventry University, London. You know.
Yes, yes, yes.
And I was coming to London from Coventry, and I was going to give a talk about transportation system of Great Britain. And finally, I was lost in tube, in metro, you know, professional in transportation system. I
see.
In metro.
I see here Vasil. Hello.
Hi, Janos.
Nice to see you.
Nice to see you too. So thank you for your agreement to give a lecture, to give a webinar to our students.
Sure, sure. Pleasure.
So it's 6 p.m. or 5 p.m. So are we ready to start now?
Sure.
A lot of people. So welcome everybody again in this virtual classroom. And today we have a chance to attend our second invited lecture. And I invite Yuri Holovac to present our speaker.
Thank you very much. Thank you, Olesya, for arranging this seminar. Thank you very much, Janos, for agreeing to meet us, to give us a talk. And for students who don't know you yet, I will say several words about you. So Professor Janos Kertes, in fact, I learned that SZ in Hungarian, one reads S. So Janos Kertes, right?
Yes.
Is the head of Department of Network and Data Science in the Central European University in Vienna. And the very university, it was founded in early 90s, last century. As I read on the site, it is based in Vienna and Budapest, and currently it is home to students from more than 100 countries. And faculty members are from over 50 countries. And for all of us working in physics and in complex systems, Professor Kertes is one of the pioneers in econophysics. Econophysics is analysis and modeling data from economy and finance using concepts and sometimes methods of statistical physics. In complex network science, he is one of those who is fathers of the science. And he was working, and still he contributes to application of fractal geometry to physical problems. Formerly, he was director of the Institute of Physics in Budapest University of Technology and Economics. And now he is the head of the department, as I told, which is Department of Networks and Data Science, which is especially important for students because they are studying networks and data science in Ukrainian Catholic University. I met Janos for the first time when I stayed in Linz, and maybe Janos remember, you were traveling from Budapest to München, and you stopped in Johannes Kepler University Linz, and you gave a talk at Johannes Kepler Colloquium. That's where we met for the first time in person. But as I remember, for the first time, I met you earlier, not in person, because I met Kertos line. For those who don't know, there is something which is named Kertos line and which is important in describing properties of many particle interacting systems in vicinity of the phase transition point. So it opens also a link to say you several works about Professor Kertész as a physicist, because he originates from physics. He was working in statistical physics of liquids, in percolation theory. Also, he is an expert in computation simulation methods, in granular systems, in traffic models. So you see there are many directions where he contributed. And I ask you, especially I ask our students at the end, so as usually, please be attentive during the lecture, but now then you will have unique possibility to give questions. So give questions and you will have the answers from the first hands. And to finish, I just mentioned several honorary degrees. Professor Kertész is a member of Hungarian Academy of Sciences. He participates in several editorial boards of renowned journals. He was Finland Distinguished Professor for some 5 years in Aalto University near Helsinki. That's where another lecturer from our group, where Vasil Palchikov worked. And because of this work, I have, you know, there is in Scientometrics, it is Erdős number. Erdős number is how many links you have in co-authorship to reach the common paper with Erdős. So I have Kertész number 2, because I have the paper with Vasil Palchikov, and Vasil Palchikov has a paper with Janos. So I finished by what I started. Thank you very much for coming to us, and I wish very much that in future you come not online but in reality. And thank you.
Thank you, Jurko, for your very kind words. It's really nice of you, this introduction. Let me ask first a question. How long am I supposed to speak?
Olesya is the boss.
So usually it's 1 hour or a little bit more. So
okay, good. So thank you very much. I'm going to share my screen with you in order to show you my slides, if I will be able to do so. Yes. I hope you can see now my slides.
Yes.
Yes.
You should make full. Yes, it's fine.
Okay, very good. So today I would like to talk to you about networks in economy and finance, but I'm starting with a little broader perspective and with this quotation from a very famous physicist, Stephen Hawking, who passed away a few years ago, who said that the next century will be the century of complexity. This he said in the year of 2000. That means that our century is the century of complexity. What is complexity? I don't dare to define what complexity is. That's a very difficult task. And if you go to Wikipedia, you will see that there is a dozen of definitions given there, which means that there is no definition. Instead, let me just list a few features which characterize complexity. Complex systems are characterized by many interacting components, by feedback mechanisms, nonlinearity, cooperativity, and emergent phenomena. So let me go now. Let me mention that in short, or in a kind of selling sentence, this can be formulated as the whole is more than the mere sum of the parts. This is characteristic for complex systems. And let me now go to economy and go through these characteristics. Naturally, economy is characterized by many interacting components: individuals, households, firms, organizations, banks, the state itself, and so on. They interact in many, many different ways, and this constitutes the economy. There are feedback mechanisms, obviously, in the economy. Let us just remember to the famous invisible hand of Adam Smith, which assures that in spite of the fact that everybody wants to perform in a way that it is good for him or her, the overall economy works and something is produced in a quasi-equilibrium so that that the demands can be satisfied. Feedback, nonlinearity, and cooperativity is, I think, very well depicted in this famous cartoon by Cal, which probably many of you have already seen. This is a day on the nation's most important financial institution, as it is said, and there somebody gives a hint on the phone that I've got a stock here that could really excel, and then people start like crazy selling the stock, and then this guy down there says that this is madness. I can't take anymore. Goodbye, bye. Oh, and again it starts. So it shows that there are really nonlinear effects, because very tiny changes can cause huge impact. And there is also a component of cooperativity there, obviously, and so on. And clearly there are emergent phenomena related to economy. It is enough to refer to the global crisis or new forms of economy. For example, the form of online purchasing or online economy is an entirely new form which emerged recently. So one can say that economy is a paradigmatic example of a complex system. Well, the next question is, what makes a system complex? And one could naively think at the beginning that maybe it is just the large number of constituents. But this cannot be so, because we know that, for example, in an equilibrium gas, there are many interacting particles. Nevertheless, we wouldn't call it a complex system. Or taking an example from a more complex world, one can say that number of genes, maybe that is what determines the complexity of a biological entity. But this cannot be true, because there are plants which have much more genes than we humans. So the crucial point should be then something else. And it is related to the way how the components, how these constituents are related to each other. In other words, to understand the functioning of a complex system, we need to map out and understand the skeleton behind it, the underlying network. This is not the whole story, of course. Knowing the network will not explain everything, but it is unavoidable to map it out. And consequently, there are many ways to identify networks in the economy. There are infrastructural networks. There are relational networks, how people are related to each other in economic action. And there are networks which we deduce from the statistics characterizing the economy. For example, similarity-based networks. I'm coming to that at the end of my talk. So let me quickly go through these infrastructure networks, which are kind of plausible. On the example of France, this is the road network of France. Here you can see the rail network of France, the water network of France, power grid, pipelines, and broadband availability. So these are all related to infrastructure. And I'm not going to deal with that. Instead, let us think a little bit about micro and macro economy. Networks are constructed such that they reflect economic relations, interactions. And this is crucial for one of the biggest questions in economy, namely how to link the micro level to the macro level. Here are the definitions of microeconomics and macroeconomics as taken from Wikipedia. Microeconomics studies the behavior of individual households and firms in making decisions on the allocation of limited resources. Macroeconomics, on the other hand, deals with the performance, structure, behavior of an economy as a whole, rather than individual markets, economy of a country or a continent. Microeconomy, by definition, considers concrete relations. When you have to decide how to allocate the limited resources, you have to take into account the interactions. So in that sense, microeconomy uses a priori network approach, at least from the point of view of what we call egocentric aspect, namely that we pick one particular element and look at the links, at the connections of this element. So at the micro level, this is unavoidable. The macroeconomy deals with aggregates, with the GDP, with unemployment, with deficit, national trade, and so on. And in the mainstream approach, what economists usually assume is that these problems can be attacked by using a so-called representative agent. We physicists say that this is a mean field approach. If you remember, those who are physicists from you, how we calculated the phase transition of the Ising model in the mean field approximation, then this was exactly what we did, that we assumed that a spin behaves as we could assume on the average. And this is called representative agent in economy. But we also know from physics that the topology, the network structure of the interactions is crucial. For example, we know that in a one-dimensional system, in a chain, there is no percolation unless you occupy all the sides. Or for the Ising model, there is no ferromagnetic phase for non-zero temperatures. We also know that percolation in a scale-free network with degree exponent less than 3, we have again PC equals 1. So, or we have to dilute the system basically by removing all the elements in order to destroy percolation. So this shows that the topology has a crucial a crucial role in how a system behaves. And Alan Kiernan was one of the first economists who realized that, and he pointed out that when we want to understand this problem of how to get from the micro level to the macro level, then we have to deal with the network on which economy is played. So economy is a social science because it's a consequence of a social activity, and therefore concepts and methods of sociology should be considered, including social network analysis. So what kind of relational networks can we speak about when studying the economy? These are trade networks, ownership networks, or overlap in board directorships, and so on. But of course, if we want to study these networks, we need data. And some data are public. For example, the ownership and board of directors data of large companies are usually public. But usually trade networks, who sells or buys what to and from whom, these are not public. But this is the economy. I mean, that is the essence of the economy, who trades what with the other parties. Fortunately, there are exceptions. Fortunately, there are cases when we can map out these networks. And then there are networks in finance, the interbank loans, then network techniques applied to evaluate correlations between prices of pairs of stocks, or networks of investors following similar strategies, and so on. In finance, data are available usually. Either they are public. If you go to Yahoo, then you can see the daily prices of stocks. If you are interested in a higher resolution, then you can buy these data. What kind of data? Trade and quote data. This contain the best bid, the best ask, last transaction price, and of course the time of it, and the limit order book, which is a much more detailed data set where all the orders are documented. So this is of course a very rich data set. But even in that data set, the agents cannot be identified. Who makes the order is not public. But there are again exceptions. For example, in Spain, in Finland, and in China, there are data sets where you can identify the players, so to speak. But this is not the whole story in finance, because there are so-called over-the-counter transactions, which are not going in the open stock market, but they result from private discussions and become public only by changing the ownership. So this is the background. And then let us be a little bit more concrete and go to the World Trade Network. This is part of macroeconomics, and data are available here. For example, in this study, which I'm referring to, the authors studied, you can see the reference in the bottom with small letters. I won't read it always. So in this paper, the World Trade Network was studied between 1951 and 2000. This is a picture of it, but of course, not all the links are shown because you couldn't see anything. There are so many links. Only the 4% of the links are shown. The 4 most important percent of the links. Here, 80 countries are there with 411 links. That is the situation in 2000. And having such a network, you can start analyzing it by the usual network analysis tools. You can have a degree distribution. You can calculate the clustering coefficient as a function of the degree, and you can check whether this is a degree associative network or not. And what you can deduce from these studies is that this network has a degree distribution which is very broad, and you can identify a part of it which is more or less linear on a log-log scale, indicating that this is kind of scale-free network. You can see also that the clustering is high, meaning that if A has high trade with B and A has high trade with C, then there is a high probability that B and C also trade with each other intensively. And this is a so-called disassociative network from the point of view of degrees. What does that mean? That means that the high degree nodes, these are the most important countries from the World Trade point of view, are preferably in connection with small degree nodes. And you will see that on the next plot or the over next plot, because before going to that, we would like also to see how the weight is distributed on the links, the weight is, of course, the value of the trade. And this plot shows that the weights are distributed in a log normal pattern. Of course, the most interesting aspect of such a study is, that was done by another group, is how this network evolves in time. And you can see here two pictures. One is from 1960 and the other one is from 2000. And this is totally different. One is, of course, a general evolution of the picture because the trade has evolved during these 40 years, and there are much more links in this picture, even much more important links, much more countries even. But if you go a little bit into the details, for example, you check where China is. Here in the right upper corner, you see Russia, and below it is China, and it is only linked to Russia. In this other picture from 2000, you can see that China has got a very central role. It is not anymore connected to Russia at all, but it is very strongly connected to the US and to many other countries. So this picture reflects really what we know anyway. In this picture, you can see the backbone structure, which means that only those links are kept which are relevant with respect to a random network at a confidence level 1 promille. Okay, so this is already interesting enough, but let us go to a more interesting question, and this is about complexity. So how to check the evolution direction of a country? Well, there are many different ways to interpret this World Trade Network, but it is natural to interpret it in terms of a bipartite network, where one set is the set of the countries and the other set is the set of the products. And one country, in this particular case, it is Italy. It produces wine, cars, and also it has a pharmaceutical industry. And the other country is Germany, with cars and strong pharmaceutical industry. And this picture was made by Italians, so they didn't know that there is also wine produced by Germans. They haven't heard about the very good quality Rhine wine. Anyway, you understand what this bipartite network means. And if you order then the countries and the products in such a way that, for example, you put in the first row those countries which have the most diverse production spectrum, and then the second, and so on, and then you arrive at a picture, what you can see here, which is approximately triangular, meaning that there are countries which are very, very diverse, and there are countries which are very specialized. There are countries which have many different types of products, and there are countries which have only one or two products to sell. And it is a question, what is better? Is it better to specialize, or is it better if you want to diversify? And in a recent paper, or a series of papers, this Italian group around Luciano Pietronero came up with a construction which measures this diversity or complexity of a product and the diversity or fitness of a country. This is the scheme they use. So you have a fitness of a country. This is the first, I don't know if you can see my cursor. I am afraid you cannot. Anyway, You see this F of C.
Yes, we can see.
You can see, fantastic. So this is the part of the formula which I am referring to. This defines the fitness of a country, which comes as a sum of the fitnesses of the complexities of the products which this country is in relationship, which this country sells to. And the complexity is then produced by this formula, where of course if a country is of a very low fitness, that means that this quantity down here is small, then of course you have a very high nominator and the contribution will be small. So this makes a lot of sense, and then finally you have to normalize in order to be able to plug into this self-consistent scheme. How you calculate it. You see, this is n minus first, this is n minus first, and this way you calculate the nth value, and if you crunch this, then finally you arrive at the fixed point. So this is the way how you calculate fitness and complexity. And here you can see the ranking of different countries according to their fitness. And of course, there are some which have very high fitness. Up there, you can see Germany. And what is remarkable, again, let me refer to China. China has changed a lot. It has increased between 1996 and 2010, its complexity enormously. And there are other countries, for example, Brazil, where an opposite trend can be observed. So this is a tool to characterize the fitness of a country with respect to this diversity. And in fact, if a country is diverse, that shows that it is indeed fit because it is able to produce goods which other countries may not be able to do. Okay, so let us go to trade networks. And I suppose that everybody has heard about eBay, which is an internet bidding company. And on this company, in order to help consumers to orientate, there is a structure. You can find a good what you are looking for in this nomenclature or tree. And you have, of course, you can define, of course, again, a bipartite graph. You have bidders and goods, and two bidders can be linked if they bid for the same item or the same type of goods. And again, this way you get a network, and you can do the usual network characteristics. You can look for the degree distribution, which you can see here. You can look for the weight distribution, which is there. And you can look for the clustering coefficient as a function of the degree and compare it with a null model, which probably you cannot see which one is. This down here, this is the null model, which corresponds to a randomized, sorry, to a randomized version. And you see there is a significant difference between these two curves or straight lines in this log-log plot, indicating that there are correlations, multiple encounters, and so on in this system. You can also try to identify communities. And indeed, this plot makes the impression that there are well-defined communities, and if you appropriately order the network nodes, then the structure of the adjacency matrix will become such a block structure. And then you can define the odds ratios, which means the probability of bidding in community C something in community C, provided the bidder is a member of cluster S, and this is divided by bidding in C, in C, provided that the bidder is not member of cluster S. Okay, so and you arrive at this colorful picture, which is a kind of proof that this block structure makes a lot of sense, because indeed people remain within a block by using this type of characteristics. Another very interesting way to use data from eBay, it was done in another paper by these Korean people, where they simply made a classification study of this bipartite network, in this case for the goods, depending on, and they are close or connected to each other when there are common bidders. And this hierarchical structure, which you can see in the upper part of the figure, is a result of an agglomerative hierarchical clustering scheme, what we use in studying network communities. And this is compared to the scheme what is used or was used at that time by eBay itself. And it shows that the intuitive clustering tree structure which was introduced by eBay is by far not the optimum one. So you can use network science, so to speak, for very practical purposes to improve selling. So let us go with trades networks to a totally different scale, from the eBay to the trade network of Japan, because that is a very exceptional case where we have data, better to say we is not a good expression because I have no access to this data, but Yoshi Fujiwara had access to this data, which is really unique, which tells about an entire economy, this relationship, who sells what to whom. And this data was produced by a company which was designed to measure credit risk, and was made available to some academic researchers, and not all, even in this fantastic data set, you have no information about all interaction, because the clients of this company were asked about their crucial partners. But even this way, the data set contains 1 million firms, the most active firms in Japan, and 4 million directional links. This is these are the most important data about the information about the data. And again, as usual, if you start with a network, you measure these typical quantities, the degree distribution, then the weights and sales, which is basically the weights, and the relationship between the in and out degrees. And what you can see here, which is beautiful, I think, for example, in this first plot, is the in degree distribution. This is a directed network because a company sells something to B company. This is a directed link, and this in degree distribution, which is the cumulative distribution, is really beautifully following a straight line on this log-log plot over almost four decades. So the clustering coefficient is very small, even smaller than a random network, which you arrive at by randomizing the network. And it is also true that the network is disassociative. It is not a big surprise that this network has a small clustering, because why should there be many triangles in a trade network? A sells something to B, sells something to C, sells something to A. That doesn't make much sense. It may happen, as you can see, it does, but with a very small density. So the next step is to identify communities. And what was observed by this community detection, which was based on modularity optimization at different levels, was that the community structure is hierarchical. And this is a nice result, because we know about the economy that it does have a hierarchical structure. Here you can see the same for the Japanese economy. You can see here large groups, large categories, but then you can zoom in, and one category like manufacturing goes then into smaller categories, and you could even continue that. And of course, when you take this trade network, in some way this trade network reflects this hierarchical structure of the branches. But one can do more. One can do more. One can try to understand how cascading failures develop in an economy. And this is a statistics about bankruptcies in the Japanese economy during different in this period of time. What is depicted here? It's basically 1 year from the end of 2006 until the October of 2007. You see some periodicities here, because Sundays nobody goes bankrupt and so on. But this is an interesting picture of these statistics. And a very important observation is, and this paper was, so to speak, one of the pioneers in this respect, that bankruptcies do not happen isolatedly. They are not isolated events, because they can cause cascades. And in some cases, a bankruptcy may be totally isolated. It can happen to a company and that's it. Or it can happen to a pair of companies and then they dissolve and the economy works further. But it may happen that one bankruptcy causes another or pair of bankruptcies and so on. And finally, an entire economy can suffer. And this we witnessed in 2008 when the global crisis happened, that was exactly caused by such avalanches. And this picture shows a simulation of such a cascading failure on the data what are present in this trade data set. So there is something happening here, and this causes a series of bankruptcies. And you can then make a statistics over how many companies are involved in a cascade that is shown here. The observation is that You have many where there is no cascade whatsoever, but then there are some which cause several further bankruptcies, and in some cases this is really an avalanche, a catastrophe. And the other branch shows a model which I'm not going into. So this is a big problem, and how big this problem is, we learned in 2008. So scientists have started thinking about what to do and how to describe this problem, and more importantly, how to avoid it in the future. And a very interesting and appealing theory came up by Stefano Battiston and his collaborators, which is called depth rank. Depth rank reminds to PageRank, and the idea behind depth rank is really similar to that of PageRank. Because what is PageRank? PageRank tries to measure the importance of a web page, but by taking into account the importance of other web pages which are connected, and they are also connected to others, and so on. And this is the logic of depth rank. What they want to calculate is the risk related to a bankruptcy, but also taking into account what it would cause, and so on, to the entire economy. And in this case, the nodes are, of course, institutions, and links are dependencies between them. And then you can calculate an AIJ weight matrix, which represent the funding of node I to J. And then there is a tier capital, of course, related to all institutions, and the threshold at which we say that this particular institution defaults, gets bankrupt. And of course, if we remove an institution, then there is a loss, AJI, for bank J. And you can calculate then the impact of I on J, which is as long as there is just a loss, it can be calculated as shown here. But of course, it cannot go beyond AJ, because then it gets bankrupt, and then we take as a value 1. And you can introduce what is called the economic value and an impact of neighbors. I'm afraid that we cannot go into details here, so I just want to signalize how this goes. And finally, you arrive again at a self-consistent system, where you can iterate the machinery and arrive at values which are the depth rank values of the particular banks. And this is shown here in 2 different cases. The distance from the center represents the depth rank. And this is the situation when everything goes fine. And this is the situation close to the catastrophe, when the depth rank has got very high for several institutions. You can see, for example, here Merrill Lynch, and which is a famous institution from this point of view, and so on. So this is a very, very sick situation as compared to the left-hand side. So one can also study the ownership networks and the evolution thereof. These are 2 pictures. One is the German company network, ownership network from 1996, and the same from 2000. You can see an enormous concentration of capital during these 4 years. and this is related to cascading bankruptcy. Of course, this cascading bankruptcy had by far not such an extent as what we witnessed in 2008. So here again, an ownership network of the Italian stock market, and you can again study these networks very similarly to what we saw before. This is the American counterpart, and then you can introduce what is called the participation ratio, known as it's a concept known from physics, and you can distinguish between the Milanese stock market and the Nasdaq or the New York Stock Exchange. And what you can see is that these American stock markets are much more inhomogeneous than the European one. The participation ratio tells that the distribution suggests a higher concentration of capital in the US. Okay, so these are characteristics for the board of directors. I want to jump over that because I would like to go to networks in the last few minutes, to networks based on coevolution. So these are networks which are not necessarily based on interaction. We study the statistics of some temporal processes, doesn't have to be economic or financial, and we see time series which have similarities, and we can use these similarities to construct networks based on coevolution or correlation. One measure of coevolution is correlation, of course. And this is a general problem of selecting significant correlations. If you have a correlation matrix, you see their elements, and it is very difficult to tell what is important and what is not. And this is exactly the problem here with different stocks. For example, they have a price evolution, and you can correlate them. And if you do it for n stocks, you get an n by n correlation matrix. So what? How to tell from that what is really importantly correlated with each other and what is just noise? And this is a general problem, as I said. Whenever you have such correlations, this question can be asked. For example, if you do microarray experiment in genetics, you have again these sequences, and you have to distinguish between important and less important correlations. So what I'm talking about here, to be very concrete, this is the New York Stock Exchange, and you have here an indicator which is one of the, this is the General Electric stock. It's time evolution. You go to the so-called logarithmic price, and finally to the logarithmic return, which is of course the difference between the logarithmic prices for 2 days, let's say. And this is an interesting pattern. It is definitely not what you would expect from a Gaussian noise. It has a clustering. There are periods when the volatility is very high, and then there are periods when it is low. There are huge outliers or fluctuations, which definitely wouldn't happen in the case of a Gaussian noise. But today I don't focus on this aspect, which is also very interesting, but on this coevolution aspect. And here you have this return matrix, that is, you have these several stocks, and these stocks have all a time evolution. For example, AA and XRX, these are 2 stocks. And now you define a time window of with t and move it over the sample and calculate within such a window the correlation. And this way you get a time-dependent correlation matrix, right? You get a time-dependent correlation matrix. The correlation coefficients are defined as usual, and you can define a distance matrix from the correlation matrix by this simple nonlinear transformation. And then you have you can say that you have a weight matrix. And you can say also that this weight matrix defines for you, if you take out from the diagonal the elements which are, by the way, taken out by this transformation naturally, so you put zeros. This is a weight matrix for a complete graph, right? Because all the elements are different from zero, that is something, and this weight is for a complete graph. And now what we would like to do is to select what is important from that. And one very simple way to do that is to say that we don't deal with the complete graph because it has n times n minus 1 over 2 links, and that's too much. We would like to see what is important, and in order to do so, we define the minimum spanning tree on this complete graph. What is a minimum spanning tree? The minimum spanning tree is a tree, meaning that there are no loops, is a spanning tree, meaning that all the nodes are in that tree, and it is a minimum spanning tree, meaning that if you sum over all weights on the links, you get a minimum. And, and that is the object which represents, at least in this approximation, the most important links. So this is such a minimum spanning tree. And interestingly, if you go to Forbes and look at the basic branches of economy, you can see that the branches of the minimum spanning tree correspond to a good approximation to these branches of the economy as described in this list. Of course, you can try to characterize this and this minimum spanning tree. And the interesting feature is, first, that it has a dynamics. On the left-hand side, you see how it looks like when everything goes fine. And on the right-hand side, you can see how it goes when there is a crisis. And you see that there is a kind of phase transition here, that it shrinks tremendously when there is a crisis. Okay, you can again characterize the different quantities. You can see that this is a very robust description. I can show you that on the example of this tree. So if we put in the links into this tree and remove them if in the next month it was not present in the minimum spanning tree. And this way you will get always less and less links, of course, but even after 3 years there are some links which have never been removed, because if we once remove a link, we don't put it back again. So yeah, this is this phase transition which I wanted to mention. And finally, I would like to mention that this minimum spanning tree representation of the most important correlations have some practical impact, because when you put together a portfolio, your intention is to diversify it, because that is the way how you can eliminate risk which is represented by the co-movement If you put everything on one asset, then you go high risk. If you put everything on another asset, which behaves exactly on the same way, you haven't reduced your risk. You have to diversify your portfolio. And what is the result of this study is that you do it the best when you put your portfolio on the leaves of this minimum spanning tree, on the outer leaves of this minimum spanning tree. And this can be shown nicely. Okay, I think I will stop here. I have a few more slides, but they are perhaps not that important, or at least I don't have time to speak about them. And I would like to stop here and ask you about your opinion and questions and remarks. Thank you for your attention.
Thank you very much for a very interesting talk. So please, anyone has question?
Okay, so
May I start?
sure, go ahead. Yes.
Yeah, I remember at the beginning of your talk, you showed some figures, some networks which were represented using the most important links. So, and several times you were talking about the distribution of weights.
Yes.
So weight
Yes.
is important. But we know from the social science about the strength of weak links.
Correct.
Can we say that this spanning tree somehow use this notion, because it is this spanning tree is based on the weakest links? Yes.
No. This is a misunderstanding. Let me try to understand to answer your question. First of all, what you refer to is a very important aspect of social networks. In fact, it goes beyond social networks. You can find such important weak links also in biochemistry. So this is very important. But the minimum spanning tree is a misleading term, because in fact it is a maximum spanning tree. It is minimum because I made this nonlinear transformation to the distance in order to have short distances. But you can stay with the correlations, and then what you would ask for would be a maximum spanning tree. So the weights which are there are high weights. So they are not weak links. But nevertheless, your point is important, because the minimum spanning tree is a constraint. So you do not have all the strong correlations. Actually, this is exactly what I wanted to show you. So maybe I show you the last figures of what I wanted to show, because that is exactly about this. Yes, here at the end. Yeah, this is it. Here. So you can see what I'm showing, right? Can you see what I'm showing?
Yes, yes.
Okay. Okay, I have to go backwards here. So this minimum spanning tree concept is a way to reduce the information, right? So we know we have a correlation matrix which is full of noise, unimportant information. And that is a way to select what we think to be important. However, we know that there must be very important correlations which are ignored. Why? Because we use this constraint that it has to be a tree. So this is another way to filter the correlation matrix, that you put in one by one the strongest, the second strong, and so on correlations. And this is what you get here. This is what you get. So here we are at the stage where the number of links is more or less the same as what we had in the minimum spanning tree. But the structure is totally different. We have a non-connected graph here, and there is a branch which is strongly connected. So what you, in that sense, you are right, that in the minimum spanning tree, there are also links which are weaker than the strongest links. They are not weak, which are weaker than the strongest links. And their role is that they held they hold the entire cluster together. Okay, so this in this sense, it is a valid point.
Thank you. So this is a very useful approach to visualization of network as well.
Yes, this is a very simple approach. Actually, calculating the minimum spanning tree is like this. It's there are very fast algorithms, and you have immediately an impression. And what is also very how to say convincing in this context, this correlation between the branches and what you see on the branches of the tree. So there is something behind that. You immediately see that.
Probably the community structure is correlated with these branches.
Exactly, exactly. So you indeed you identify in a very cheap way, so to speak, some communities.
So I guess Ralph Kenna has some question.
Sure.
Ralph, maybe you should put your question on your own.
I have a question, but I don't know if you can hear me, because
yes.
You can hear me okay?
Yes.
Okay, I wanted to know if how is it's a very general question. How is everything received in the economics community? Do they like econophysics, or are they afraid?
Okay, so well, this is not an easy question for two reasons. One is that econophysics has grown and has got very branched, and it's not anymore so easy to define what it is. For example, I have recently worked with a student of mine on corruption problems, because that is also very closely related to networks, of course. And I can ask then, is that econophysics or not? Very difficult to tell. In early times, in the 90s, we mainly did financial analysis. And if your question is focused on that, how that part of econophysics is taken by economists, then I should say that it is mixed. And it depends on whom you ask. Economics is a very conservative community, economy. There is the mainstream economy, right, which is still mainstream, which is based on this assumption of a representative agent. And in many of the departments, this is what they have. And this is, of course, a very interesting and intellectually challenging approach. And you can do a lot of work on that. And in many cases, this is valuable and works well, only if something happens, so to speak, like a global crisis, then you run into trouble. But there is an increasing part of the economists who take it more and more seriously, not necessarily by referring to econophysics, but by doing similar things. And for example, Alan Kirman, whom I referred to, is definitely somebody who is a very well-known economist, who is valuing very high the contribution of physicists.
Ralph, are you happy with answer?
Yeah, yes, I am. Thank you. I only heard little bits because now it's just after work time in England, so everybody's coming home from work and looking at the internet.
Okay.
But thank you. Okay, thanks.
May I ask a very small question,
Sure, go
continuing
ahead. Yes,
this
Please do so.
your reply? Is it possible in principle to predict cascades and at least to describe these cascades using that mean field theory? Is it possible?
Yeah.
Is the notion of cascade is something which can be seen only when you use this new econophysics?
I have to think a little bit. Well, first of all, I should say that systemic risk, which is basically this cascading risk, that this interdependence of the different banks, and in fact, this is just one layer of the economy, because the banks are also connected to the industry and to the households and all this. This is, but this interconnectedness is something which is not really taken into account in a proper way in mainstream economy. So what you can expect from mean field type of approaches is that at some point a solution becomes unstable. That is at most what you can. This picture what we have here is very much based on our network type thinking, right? And if you don't have a network behind, then you cannot really describe. For example, you have an accelerated spreading of in such a cascade, and that is due to the forth and back motion in the network. And I cannot imagine how that can be taken into account in a simplified description. It's not a simple question either.
Thank you. Do we have some other questions? Maybe some of our students, so they are supposed to make some, to choose a network for analysis. So maybe somebody choose something close to economic.
Yes. In any case, I will send you the slides so you can use them.
Thank you. Thank you. So
I think I have a question. Can I ask?
Yes, of course.
Yeah, so thank you very much, Mr. Curtis. It was very exciting lecture. Like the part I liked most was about the trade network, and actually some like part of this I'm sorry. Yeah, it was slightly connected with the network I'm working with. I also have a network where I have a fully connected network where all the nodes are possibly connected with all of the other nodes. And I have some measure of a strength of this connection. And with the trade network, as far as I understood, you picked 4% of the, or a scientist picked 4% of the most important connections, yes?
That was shown indeed, yes.
Yeah. And I was thinking a lot about my own network. Like, one of the approach would be to pick like just the strongest links. But what could be other alternative approaches? Maybe
Yes.
like other types of connections.
I understand. Yeah, and this is really a closely related question to what I was talking about. There is another thing which I mentioned, and that was that you can shuffle the weights. Okay, you can randomize, and then you can ask for what is significant. And this way you can also try to identify what are the most important connections. But you can also take this approach, what I explained last, and try to build the maximum spanning tree, right? So what you do is thresholding, right? Or what I mentioned with this 4%. You start with the strongest and you go lower and lower, and then stop at some point, which is your threshold, which is a legitimate way. You can go that way. But you could also say, okay, this way I ignore perhaps some important, less strong links, and maybe they are better captured by this tree approach. There are other ways also. For example, you can extend this tree approach by what is called the maximum planar graph. I don't know if you know what a planar graph is. Do you know, Petro?
I'm
A
not
planar
sure.
graph is a graph which you can draw without crossing two edges. Okay?
Oh, yeah, I understood.
This is a planar graph. And a tree, of course, is a planar graph, right? Obviously, a tree is a planar graph. But you can add to this tree links. But you can, but you don't want to add all the n square minus, I mean, all the n square links. But you can add links which you can draw on a plane without crossing links. So and there is a method to do it to a limit which is called the maximum planar graph. And there, if you are interested in that, you can write me an email and I will tell you the reference where you can find literature to that.
Yeah.
How many nodes do you have?
Depending, like from few hundreds to 30,000.
Okay,
Like,
that's a lot.
for
That's a
different
lot.
types of data.
Then
Yeah.
you have to somehow reduce the dimension. Yes.
Yeah. Yeah, but thank you. I will definitely try some of those approaches.
Okay, very good. Welcome.
So do we have some other questions? Please use your chance.
Yeah, maybe it's too late in Ukraine already.
It's not too late, but it's already, yeah. May I put another question?
Sure.
sorry, I'm too active, but does it make sense to use a temporal network approach, like to, you already showed this sliding window technique. So
Yes.
maybe this is also a kind of way to study this big
Yes.
dense network, but when you consider on the small slice, you can see the structure. So does it make sense to simply to consider the network for different time periods separately, something like that?
Yes. So indeed, when I discussed this correlation-based network, then I introduced in a way temporality by removing the links which do not occur in this particular time window. But what is more interesting is to use this approach for the trade network. What would be more interesting, right? I mean, that would be really very interesting to have data about not only who sells what, whom, but when. But this is something which we can dream of, but we don't have the data for that. So this is certainly something which would be very, very useful. And if somebody has such data, I don't know if Petro has temporality in his data, but that would certainly be worth studying, because one of the features of economy is seasonality and these cycles and all, and for that such an aspect is crucial. But as far as I know, no such data are available.
It's a general problem.
General problem, indeed, yes.
Thank you.
Okay, good.
Thank you
So
very much, Janos.
thank you for the
very
opportunity.
interesting lecture.
Good. So, and I will send you the slides, and then you can distribute if you wish. Okay.
Thank you. Thank you very much. It
Bye.
was very nice to see you and to hear you.
Bye-bye.
Bye.
Thank you. Bye.
Bye-bye.
Goodbye.
Yeah.
Thank you. Thank you.